So today's lesson is going to be focusing on double and half angles. I'm going to explain a little bit about what those are. So first you can take a minute, if you have to you can pause and copy down these double angle identities. So double angle means that the angle you're actually calculating something about might be 120, but instead of writing it and calculating things directly about 120, you would rewrite 120 in a different format, like 2 times something, in this case 60, and you would use 60 to complete your calculation about 120. Now the reason you see 3 formulas written for the cosine of the double angle is because notice it used cosine squareds and sine squareds in its formula. And if we go way back to the first thing we did, those Pythagorean identities, you can replace the cosine squareds and sine squareds and rewrite them in different formats. So that means there's 3 ways that might be useful to write that one formula. So why these work, and again, if you need to copy them down, pause. Why these work basically comes from the idea that, sorry, I'm not going to use tangent, I'll look at sine. Double an angle is like adding 2 of them together. So another way to write 2 theta would be theta plus theta. So I'm focusing on this one right here. I could write this like that, and we already have a sum formula. Your sine sum formula said it would be sine of the first angle times cosine of the second angle plus cosine of the first angle times sine of the second angle. Normally these don't combine together, but in this case, since the angles are the same, this term and this term are really the same thing. They're both sine of an angle and cosine of an angle multiplied together. So this makes 2 sine thetas, cosine thetas, and that is our double angle formula. So those just come from using that sum. The half angle formulas are grouped together with these because they're kind of for the same purpose. For example, let's say somebody wanted to ask you to calculate sine of 15. Using what you know about special triangles, you would feel like 15 is not something that you could calculate with using special triangles because we don't have a special angle of 15 degrees. However, you could think of 15 as 30 over 2. It's still worth 15, but you've written it in the format of half of an angle. That you're, instead of just using 15, you're going to use 30 in this special formula where it's calculating stuff about 15, but using a 30-degree angle. So our sine formula for those half angles, and I'll explain about the plus or minus here in a minute. 1 minus cosine theta over 2. So again, what this means is if you were trying to calculate sine of 15, but you thought about 15 as 30 over 2, 30 over 2 would be on this left side, and it's really worth 15. But what you'd be plugging into the right side over here would be just the 30 without it being split in half. That's what this formula allows you to do. Cosine of theta over 2 looks really similar to the sine. And then there's tangent. And while you guys are writing these down, just like an expectation thing as you guys move forward, our normal expectation is that students will memorize all of the formulas in this unit except the sum and difference ones. We usually do provide those for you. They're just not used as often in calculus. You still need to be aware of them, but these other ones come up so often that you have to substitute them out that they feel as though you should really know them on your own. Okay. The half angle is a little more complicated to prove why it works. It's a little bit more like a mathematical proof you might do in college if you were proving some theorems. So you start with a statement assigning a value to something. So theta is one angle, and it's equal to alpha over 2, where alpha would be another angle. This would be like saying, I want to find stuff out about 15, but I could write 15 as 30 over 2. So 15 would be like my theta, 30 would be like my alpha. Okay? And then I'm going to take my double angle formula. So I'm going to pick one version of the double angle formula. So right now I'm just writing the formula. Okay, there's a statement that we know is true. And now I'm going to plug this in. theta is an angle that could be replaced with alpha over 2. And let's look at what happens when I do that. So I'm replacing all the thetas with what they're equal to, which is alpha over 2. In here, this is all happening in the angle. These 2's cancel, and this now just says cosine of alpha. You cannot cancel these other ones. They're the only thing inside the angle. And remember what my goal of this was. I was trying to show you how they would have derived a formula for the half angle. So their goal would have been to get this half portion alone. So to do that, I'm going to add 1 to both sides. And then I'm going to divide by 2. Now that's for the 2 outside of the cosine. It can't really affect anything that's inside of that trig function. Then lastly here, this is a good formula except for that this is squared. So if I don't want that squared, I'm going to rewrite it like this. So cosine of alpha over 2 equals plus or minus, because I square rooted both sides to solve this. And that's how I would derive it. So you could do some version of that to derive all of these formulas here. We're not going to keep doing that, but that's the case. The next thing I want you guys to do is make a big note next to these formulas about the plus or minus. Okay? The plus or minus is not both. You need to decide plus or minus based on angle location. And make sure you're picking the right angle. So let's say I ask you sine of 15, and you go and you start using all this half angle stuff. Before you start, or you can reevaluate at the end, you actually should already know, is the sine of 15 going to be positive or negative? Think about where 15 is located. 15 degrees would be located in quadrant 1. The sign in quadrant 1 is positive, so it wouldn't be negative. This is what you should be able to figure out. So the plus or minus in these formulas doesn't mean both. It means one or the other, and that you have to make that decision. The calculation doesn't find the sign for you, the plus or the minus portion of it. So now we're going to see how to use those. Our first example is to derive this. We talked a little bit about this already. This is the tangent formula, so you can actually use this formula in future proofs, but derive means, yeah, we know it's an identity. We want to show us you understand why it's an identity. And I'm going to start on the left side because we already talked about being able to rewrite that 2 theta as theta plus theta, and I'm hoping that's going to help me derive this. So I'm not rewriting the right side, I'm just working on the left side. So if I go back to my sum and difference formulas, the tangent formula said use tangent of the first angle plus tangent of the second angle, divided by 1 minus tangent of the first angle times tangent of the second angle. Now, normally this doesn't simplify so nicely, but because the first and second angle are the same, that allows that numerator to just combine together those 2 like terms. And in the denominator, those 2 multiply each other to make tangent squared. And that's what we were looking for. Okay. All right. The next example is to find the exact value of sine 270. Now, you might think I'm a little crazy because you might be like, Ms. Dahl, I already know sine of 270 because I know my unit circle. That's great. The purpose here is not really to get you to do the calculation, but really to understand how to use the double angle identity correctly. So, you're calculating sine of 270. So at the very end, your answer is going to say sine of 270 equals, and you're going to have a numerical answer. However, how you're going to solve this is to use a formula where 270 is replaced by something, and we want to use double angles. So we want to rewrite 270 as a double a number. And in this case, that number would be 135. So what this means is we are calculating something about 270, but instead of going straight to 270, we're going to use this double angle identity. For sine, we're using this one. And the angle we're going to be plugging in is not 270, because this whole thing is 270. Instead, we're thinking of 270 as 2 times 135. So the number we're using in these slots is going to be that 135. So my calculation here is going to be that this is equal to 2 times the sine of 135. Then the formula says to multiply that by the cosine, and again the angle I'm using is 135. I'm color coding this to make sure the angle stands out to you, that my answer is about 270, but I'm doing calculations at angle 135. So this is 2. The sine of 135 is rad 2 over 2, and the cosine of 135 is negative rad 2 over 2. And then I'm just going to simplify this, so those cross out. Rad 2 times rad 2 is 2. And in the denominator have a 2, and that's equal to negative 1. So sine of 270 is negative 1, but I calculated it this time using the help of angle 135 and the double angle formula. All right, example 3 is to verify. So I have to prove one side's equal to the other. As I look at this, I know I can substitute out sine 2 theta with 2 sine theta cosine theta. Like that's what I'm thinking in my head. But then I wouldn't really know where to go from there. There's a lot more on the right side. So I think here's my goal. I think I'm not going to work on the left side, that I'm going to work on the right side, eventually hoping to get to a spot that says 2 sine theta cosine theta, so that the next step after that can be to change it to the sine 2 theta. So then what to do to the right side? So I see a couple different things here. I know tangent can be sine over cosine. Notice that both these terms have a tangent in them. That makes me want to factor a little bit. Like if I write the tangent as its own factor and look at what's left, am I going to be able to keep going? So I'm going to decide to try that this time. So I'm going to factor out 2 tangent theta, because that's the greatest common factor from both terms. In this first term, that would leave 1. And in the second term, it would leave minus sine squared theta. Okay. Now, this gets me a little bit excited here because 1 minus sine squared theta takes me back to my Pythagorean identities, and I know it's got to be related to something. If I'm kind of scanning through my head, here was the original Pythagorean identity. If I rearrange it, I can get 1 minus sine squared on the right side, and it would be equal to cosine squared on the left side. So I can replace 1 minus sine squared with cosine squared. All right, so that's better. I mean, because remember, my goal is looking for something like this before I take that last step, and it at least has the 2 there now, and it has 2 things multiplied together. So I feel like I'm making good progress. The next thing I want to do is, the only thing here I feel like I can rewrite is tangent. So tangent could be rewritten in fraction form as sine over cosine. Now notice this is very helpful actually, because cosine can cancel out one of those, and then I actually have what I was aiming to get, 2 times the sine of theta times the cosine of theta, which is that identity I was looking for to transform my problem into sine of 2 theta. All right, the last couple examples that we're going to talk about involve half angle. We have to make those decisions about the plus or minus, and the formula is a little complicated. So make sure you jot down any questions you have and you ask either by sending me a message on a discussion board or during our Wednesday meetings. So in example 4, we're going to find the tangent of 195. So remember, our answer is literally going to say tan of 195 equals, and then I'm looking for something to write in my answer here. Now 195 is not a special angle. There might be multiple ways to do this if you're given like free reign to do whatever you want. Here it specifically said to use half angle identities. So I do want to calculate something about 195, but I'm going to write 195 in a different way, specifically as half of some other number. So what number is half of 195? I mean, if you're really struggling with that, you can write a little equation here. You'd see that you would times it by 2, so it turns out to be 390. 390 is what I would cut in half to get 190. So writing it in this way allows me to use the tangent half angle formula. So it says plus or minus square root, and then it says 1 minus cosine theta, or alpha or theta, whatever you want to call it. So alpha is not 195, it's 390. And then it's 1 plus cosine of 390. So 390 is basically like a 30-degree angle. They're coterminal because it's like one whole time around the circle and then 30 degrees. So the cosine there is rad 3 over 2. So this is 1 minus rad 3 over 2 over 1 plus rad 3 over 2. That is not a simple arithmetic problem, but it can be simplified at least a little bit further. We've struggled with this a little bit, so I'm going to take it off to the side. So you guys have 1 minus rad 3 over 2 over 1 plus rad 3 over 2. A lot of you guys like to jump straight into the division. You cannot do that until this whole numerator is just one fraction and the denominator. So in the numerator, if I want them to become one fraction, I need the 1 to have a common denominator with the rad 3 over 2. Then it combines into one fraction, which is 2 minus rad 3 over 2. And I'm going to use this same train of thought with the denominator. I need to rewrite 1 so it would have a common denominator, and that becomes 2 plus rad 3 over 2. So really, this previous division problem I had is like 2 minus rad 3 all over 2 divided by 2 plus rad 3 over 2. And now I'm going to do some more work with that. I'm going to write it out horizontally for you guys that struggle with this fractional division. So this is 2 minus rad 3 over 2 times the reciprocal. The 2's will cancel, and this will leave us with 2 minus rad 3 over 2 plus rad 3. So I'm going to go back to our problem. So this is plus or minus the square root, and I got 2 minus rad 3 over 2 plus rad 3. So the number part is done. The answer is this very complicated radical. And then the question is it plus or is it minus? You have to make that decision. So remember, what are you calculating? You're not really calculating stuff about 390, even though you were using 390. Really, your answer and your calculation is about an angle that measures 195. Think about where 195 is in terms of the quadrants on the circle. So first quadrant goes from 0 to 90 degrees. Second quadrant goes from 90 to 180. Third quadrant goes from 180 to 270. 195 would fall in that category. So 195 is in quadrant 3. In quadrant 3, the cosine value is negative, the sine value is negative, the tangent value is positive. So the tangent of 195, since 195 is an angle in the third quadrant, will be positive. So I'm not going to write a sign in front of this radical because it should be positive, and that is my answer. So I decided positive, not negative, based on the location of 195, since that was what this problem was really all about. Okay. In number 5, we're going to be doing the same thing, but just with a slightly different set of information. So you're given information about theta. You're given sine of theta equals negative 5 over 13. You're given that theta is between 360 and 270. But you're asked to find the tangent of theta over 2. So lucky for you, the half angle formula relates those things together, right? The half angle formula says the tangent of theta over 2 can be calculated with this formula that uses theta, not cut in half. So you're going to have to keep straight what you're calculating and what your answer is and what you're plugging in. So to find your answer, you really need this piece of information. This piece of information is about theta. That's what these things are about, so you can use them to help you. So just so we don't lose track here, everything I'm writing right here is about theta, not theta over 2, theta. Theta is in the fourth quadrant because theta is between 270 and 360. So theta is somewhere over here. I'm going to actually draw the triangle. The reason being is look at what it told me about the sine of theta. It told me it's equal to negative 5 over 13. That's not a special triangle value, so that goes back to those unit circle problems where when it was something like this, I'd want to draw it. So sine equaling 5 over 13 means opposite over hypotenuse, or y over r is 5 over 13. So the y is 5 and the r is 13. And given that it's in the fourth quadrant, the y would be that negative value. You can do Pythagorean theorem to find the other side of this triangle, which would be 12. And it would be positive given the quadrant. Looking at this picture, I can find out lots of things about theta. I can tell you that the cosine of theta is the x over the r, or 12 over 13. Sine of theta is the y over the r, or negative 5 over 13. And tangent of theta is the y over the x, or negative 5 over 12. The information from here that I need for this problem is right here. Cosine of theta is equal to 12 over 13. That's the value I can plug in everywhere it says in here to use cosine of theta. So I can move forward one step by plugging in 12 over 13 as my value for cosine of theta. And again, I'm going to go off to the other side and work out the arithmetic because it just requires you guys to go through some fraction math. So in the numerator, you have 1 minus 12 over 13. In the denominator, 1 plus 12 over 13. Again, if you want to change these, you need one fraction here. So I'm going to change 1 into 13 over 13. So that looks like 1 over 13. Down here, again, I'm going to change 1 to 13 over 13. So that's going to look like 25 over 13. So now my problem in a simpler form says I have 1 over 13 divided by 25 over 13. And I'm going to write that out horizontally so you can see the arithmetic involved. So that becomes 1 over 13 times the reciprocal, and it becomes 1 over 25. Okay. So I'm going to go ahead and I'm going to plug that back in. So this becomes 1 over 25. The square root of 1 over 25 is 1/5. So I have part of my answer that I was looking for. To answer their question, I was looking for what is tangent of theta over 2. I feel really close. I have a calculation done that says that tangent of theta over 2 is equal to 1/5. The question becomes, is that positive 1/5 or negative 1/5? Okay. Now, be very careful about rushing to conclusions. A lot of people will look over here, they'll see tangent 4, and they will say that that means the tangent is negative because in the fourth quadrant it's negative. But remember, this picture right here is not for theta over 2, it's for theta. That's not what this is about. So you need to think about if theta was cut in half. Okay, so I'm going to write this out again. So far, you knew that theta was in the fourth quadrant because they told you in the problem that theta was between 270 and 360. If you know that an angle is between 270 and 360 and that angle gets cut in half, think about cutting in half the boundaries to see where your angle lies. This means when your angle is cut in half, the highest it can be is no longer 360. 360 cut in half would be 180, and 270 cut in half would be 135. So theta over 2 is between 180 and 135. 135 is here, 180 is here. So this angle that we're actually trying to calculate the tangent for is in this area. And the tangent in that quadrant, that's quadrant 2, the tangent in that quadrant would be negative, so this will be negative 1/5.